Hi dear students, I hope you all are doing great. Do stay in a pink of health. Okay, have a great time. So let us start our today's topic, that is thermodynamics. So my dear friends, what is thermodynamics? The branch of science which deals with interrelationship of heat and work with chemical reactions. So my dear friends, let us understand what is the interrelationship of heat and work with chemical reactions. So let's take an example here, my dear friends. So in order to make you understand this term, interrelation of heat and work with chemical reactions. Let's understand this term first. Okay? So the thermodynamics will deal with the interrelationship of heat and work with chemical reactions. Let's take one system here, a closed system we will take on, my dear friends. Let's take a closed system. Let's fit this system with a piston. So let us use piston here. Correct? So this is the piston. And this is our closed system, my dear friends. Now look here, my dear friends. The pressure right from here will be the atmospheric pressure. Let us call it as P external. That is what we call it as external pressure. And this external pressure will be due to the atmosphere. Correct? So now, my dear friends, this pressure which is onto the piston downwards is nothing but P external. That is external pressure due to atmosphere. And now, inside this particular closed system, okay, we can have a gaseous substance or we can have a mixture which can undergo chemical reaction, my dear friends. Let us suppose we have a mixture of A plus B. Gas A and gas B we have here in this system. So two gases are present in this closed system, or closed vessel we can also tell, or closed container we can also tell. In this closed container we have two gases, A and B. This gas A and B, they will exert the pressure on to the piston upwards. The pressure due to these gases onto the piston will be upwards, and this pressure is nothing but it is PIN. PIN here stands for internal pressure. So PIN is nothing but internal pressure due to gaseous molecules. Okay, so which gaseous molecule we have here? A and B. So we have here two gaseous molecules, A and B type. Two types of gases we have. So they will exert the pressure onto the wall of the piston, but that force will be upwards, that pressure will be upwards, and that pressure I told you is the internal pressure, P internal due to B, and here it will be P internal due to A. Correct? So this is the internal pressure. Now my dear friends, for this closed container, if P internal, that is internal pressure, if P internal is equal to P external, then the system will be at equilibrium. That means this system will be at equilibrium. So that will be the equilibrium state. That means if internal pressure, which is just trying to make the piston to move upwards, and there is external pressure which is trying to make the piston to move downwards, if both are equal, then the system, this entire system will be at equilibrium. Yes? So that means the volume of the system will be constant. So it will have a constant value. I hope you are understanding, my dear friends. Let us suppose this is the volume of the system from here to here. So let us call it as VI. Right from here to here, let's suppose this entire thing is the value. This is VI. We call it as initial volume of the system. Don't take this as a volume. I am talking about whatever is present inside, let us call it as VI. Okay, that is initial volume of the system. Okay. So my dear friends, if the chemical reaction happens between this A and B, let us suppose there happens a chemical reaction between A and B. Let's have a look. Let us suppose between A and B there takes place a chemical reaction. Yes, this is gaseous, this is gaseous. Correct? So now they are giving me gaseous substance C. But they are giving me 3 moles of C, let us suppose. This is also gas. Now you can just tell me here the number of reactant molecules. But which reactant molecules? This NR stands for number of reactants. In which state? Gaseous state. How many reactants are there? 1 mole and this also 1 mole. So we have 2 moles here. Now if you look at the number of product molecules as gaseous molecules. So number of products as gaseous molecules. How many products are at gaseous molecules or how many moles are at gaseous molecules? 3. That means when this chemical reaction takes place, what happens, my dear friends? In this chemical reaction, 2 moles of A and B, means 1 plus 1, that is 2. 2 moles of A and B are changing into 3 moles of C. So that means the number of moles of reactants are 2. And now the number of moles of products are what? 3. Now my dear friends, what will happen when the number of gaseous molecules are changing? Reactants have only 2, but products are 3. That means reactants are changing into products. That means 2 moles are changing into 3 moles. That means here in this process, 2 moles are changing into 3 moles. Yes? That means the number of gaseous moles are increasing. So when number of gaseous moles are increasing in the system, then what will happen, my dear friends? Here I have 2 moles A and B. So when the 2 moles of A and B are there, at that time what happens? The P external was equal to P internal. So system was at equilibrium. And let us suppose that VI, which was here, it's an initial value. Correct or not? But now these 2 A and B, you can look here, this A and B undergo chemical reaction and they are changing into the product C. But how many moles? 3 moles, 2 moles are changing into 3 moles. That means inside this container we have now 3 moles of C. 3 moles of C. When we have 3 moles of C, what will happen? The internal pressure will increase. Because here it's a pressure due to 2 moles. But now the pressure inside the container will be because of 3 moles. So the pressure will increase because number of moles are changing from 2 moles to 3 moles in a chemical reaction. So when internal pressure will change, means it will increase. When internal pressure increases, what is the possibility, my dear friends? That internal pressure increases, that means this internal pressure will become greater than external pressure. Then the volume will also change, means now this internal pressure will make this piston to move up. Because internal pressure is more now. So now we will get the final value. Because it was the VI. When this piston will move little upwards, then we will get VF, that is final value. So the change in value will be written as what? VF minus VI, that is final value minus initial value. I hope everybody has understood this thing. Let's have a look. So my dear friends, if we draw this once again, have a look. This is the piston right out here. Let's suppose this is the piston. And this was which pressure? P external, external pressure onto the piston downwards. And this was which pressure? P internal. And P internal pressure was because of 2 gaseous substances, gas A and gas B. Yes? Then I told you that from here to here, this is the value. Let's represent it outside. So the initial value is here. VI is the initial value. Correct? So we know that in this state, at this point, let us suppose P internal pressure is equal to P external. But after the chemical reaction, A and B is changing into C. Here we have 2 moles, 1 mole of A and 1 mole of B. But now in next situation, now in next condition, have a look. We will have a system with a particular piston. Let's call it as point A. Just for understanding, let's call it as point A and point B. Yes? From A to B we have a value Vi, correct? Now what is happening here, my dear friends? Internal pressure is here greater. We know that P internal is greater than P external. So when P internal is greater than P external, what is going to happen, my dear friends? What will happen in this system? Because here we will have C. Because A and B has reacted. These 2 molecules have reacted and they have given me C. But C is how many moles? 3 moles of C. Here pressure is due to 2 moles and here the pressure is due to how many moles? 3 moles. So that means the 3 moles will exert more pressure on the piston. So that means internal pressure will become more than which pressure? External pressure. So that means piston will move little upwards. When piston moves upwards, now tell me, my dear friends. So this is equilibrium state. Okay. Now look here. As P internal is greater than P external, so volume will increase. Okay. Volume will increase from Vi to Vf. That means this is initial value and this is final value, because internal pressure is greater than external pressure. Yes. So my dear friends, if you look here, let us suppose this was the initial value. From here to here it was Vi. Let's suppose this is A and this is B. And now this is the piston. Piston has moved from this point B to C, let us suppose. So this is your initial value from here to here. And now from here to here, from A to C, we will have which value? The final value is here. So which value is greater? The value Vi is greater or Vf is greater? Vf is greater than Vi, because the P internal is greater than P external. And now piston will stop here. Once the piston stops here at point C, understand that now again P internal has become equal to P external. So what I want to make you understand here, my dear friends, is that when chemical reaction has taken place, 2 moles of reactants have changed into 3 moles of products. So internal pressure has become greater than external pressure. Due to that increase in internal pressure, the gaseous molecules will hit the piston and piston will move up, because pressure inside is more, because you have now 3 moles of C inside. So due to that, what happens? Value will change. Value will change from Vi to Vf, initial value to final value. So when the value changes, that means piston is moving up, correct? That means you are doing the work. So my dear friends, work is being done here. Okay, as volume changes, that means work is done. Okay, I hope everybody has understood this particular factor or not. So my dear friends, if I tell here the work is done or not, yes, work is equal to the pressure multiplied by change in value. And you know that internal pressure is greater than external pressure. Okay, so change in value is written as Vf minus Vi. That is final value minus initial value is nothing but delta V. That is change in value. So once again I am telling you, due to this chemical reaction, 2 moles are changing into 3 moles. So pressure was here because of 2 moles. And we know that it was at equilibrium. P external was equal to P internal. So it was at equilibrium state. But when 2 moles have changed into 3 moles, now you can see here, A and B has changed into C now. We have 3 moles here. So internal pressure will be greater than external pressure. So internal pressure is greater than external pressure. So this is our initial value, Vi. When this internal pressure will make the piston to move upwards, value will change. That means value will increase. Look here, as P internal is greater than P external, so value will increase from Vi to Vf. So if this is a Vi value from point A to B, Vi value, actually you have to think inside. Yes, this Vi is the value, this line and this bottom, between them. Between A and B there is an initial value. But as the piston has been moved upwards, value has increased it. Now the final value is AC. So that AC is the final value Vf. So what is the change in value, my dear friends? Delta V. Change in value is V final minus V initial, my dear friends. And when we look at the work has been done here or not? Yes. Work is equal to pressure into change in value. And we know that change in value is equal to Vf minus Vi. I hope everybody has understood. Okay, please make note of it. Dear friends, you have understood now, due to increase in the internal pressure, in this process you have seen, due to increase in internal pressure, that's how work was done by the system. Work was done by the system. How the work was done by the system? By changing the, value from Vi to Vf. So, by changing the value, that means work is being done by the system. Okay? When internal pressure was greater than which pressure? External pressure in this chemical reaction. We can understand this chemical reaction by one more way also. Have a look. Let's try to understand this chemical reaction by one more way. Now look here, my dear friends, let us suppose this chemical reaction is exothermic reaction, and during exothermic reaction heat energy will be produced. Yes? So during this reaction heat energy is produced, let us suppose. Correct? So let us understand that how work will be done through heat energy. Yes? So my dear friends, when heat energy is produced in this chemical reaction, yes? So inside this system, heat energy will increase. So heat energy is produced in the reaction, so heat energy increases. That means the kinetic energy of the gas will also increase. When kinetic energy of gas increases, that means internal pressure will also increase. When internal pressure will increase, then what will happen? P internal will become greater than P external. When P internal becomes greater than P external, then value will change. Value of the system will change. Value of system will change from Vi to Vf. Vi to Vf is nothing but here it's an increase in volume, or you can also call it as expansion. Expansion will happen. So volume of system will change from Vi to Vf. That means when volume changes, due to change in internal pressure, volume changes. That means due to pressure, there is a change in volume, and that is nothing but it's a work done. So my dear friends, heat energy produced in this chemical reaction, look here. This heat energy of system, when heat energy is produced here, that means heat energy of system will increase. Means inside this, heat energy will increase. Due to increase in heat energy in this system, what will happen? Kinetic energy of gas will increase, and internal pressure will also increase. Then internal pressure will become greater than external pressure. Then due to this greater internal pressure, volume can shift from Vi to Vf. That means volume of the system will also increase from Vi to Vf. That is expansion of gas will happen. So when volume changes, that means work is being done, because work is equal to pressure multiplied by change in value. And you know that it is P, change in value is Vf minus Vi, final minus initial. So now there are two things in this thermodynamics. One is basically called as work done by the system and work done on the system. Right now work is being done by the system. Yes or no? So it is taken as negative. Later we will explain that how this work can be taken as negative. So my point was here, interrelationship of heat and work with chemical reactions. My dear friends, I hope you have gotten some idea. Okay? So my dear friends, let us talk about some important terms here. Important terms in this chapter. Important terms. First of all, we will write down system plus surroundings is equal to universe. So let us define these simple terms here before entering into this chapter. We'll be talking about the laws of thermodynamics as well. 0th law, 1st law, 2nd, 3rd law. So please have patience. Okay? You will understand each and everything, but with time. You need to have some patience. Okay? So system, first of all, we will see what is system. So my dear friends, system, the part of universe which is under experimental investigation. The part of universe which is under experimental investigation is known as system. Okay? Is known as system. So my dear friends, we are talking about here the thermodynamic system. Please remember that. So the part of universe which is under experimental investigation is known as system. Correct? Then what is surrounding? The remaining part, surroundings, is nothing but the rest of the universe. Means remaining part of the universe. Because universe is made up of system and surroundings. I told you the surroundings is that part of the, system is that part of the universe which is under experimental investigation. So the remaining part of the universe, that means the rest of the universe, is surroundings except system. So if you leave the system, whatever remains there, let us suppose this marker is the system. So whatever is around the marker, that will become the surroundings. If I am the part of the system, whatever is around me, that is my surroundings. Yes or no? So my dear friends, system is the part of universe which is under experimental investigation. And the surroundings is the rest of the universe is surroundings except system. Okay, my dear friends? So let us understand it in a very simple way. Let us suppose if this thing is the system here. And whatever is here around the system, that becomes the surroundings. So this entire thing is surroundings. And if this is the system right up here. So my dear friends, there is one more point called as boundary. Between system and surroundings, there can be an imaginary boundary or there can be a real boundary. Let us understand that. So let's have a look. Have a look here, my dear friends. System is separated from surroundings by boundary. So which thing separates the system from surroundings? System is separated from surroundings by boundary. Now this boundary can be of two types. You can have a real boundary or you can have a imaginary boundary. So let's talk about real boundary and imaginary boundary here, my dear friends. Have a look. First of all, we'll take the real boundary and then we'll take the imaginary boundary. See here, if we talk of real boundary, have a look here in this case. Let us suppose I will take one copper vessel. Copper vessel. Yes. Now my dear friends, once I take the copper vessel, so we will need to talk about the real boundary. And who is the real boundary here? This thing is the real boundary here. This one. This is the real boundary. Inside the copper vessel, we may have some solution here inside, some mixture of gases we can have inside. We can have here rust nut juice also. We can have here lemon water also. That lemon water, that rust nut, yes, or any gaseous mixture which we have inside here. Okay, that becomes what comes system. And this boundary is basically of which vessel? Copper vessel. And this boundary is between system and surroundings, my dear friends. This is surroundings. So this is the surroundings and this is inside the system. Let us suppose inside this particular copper vessel we have, let's suppose it's a closed copper vessel. Let's suppose it's a closed copper vessel. Inside this we have boiling water. Let's suppose boiling water. So boiling water is nothing but it's a system, correct? And this is the boundary, and this boundary is basically made up of copper only because it's a copper vessel. So this is copper boundary here, and this is real boundary, my dear friends. Okay, so boiling water is your system, this is the boundary, and this boundary is a real boundary because it's made up of copper, correct? It can be made up of aluminium also, it can be made up of wood also. Yes, so real boundary can be your copper, aluminium, zinc, yes or no? It can be even wood also, it can be your glass also, it can be plastic also, it can be rubber, but it should be real. Boundary should be real. Okay, now let's talk of imaginary boundary, my dear friends. Imaginary boundary basically here I will tell you, try to understand. If I have a coal with me, let's suppose this is a coal. Yes. And this coal is our system. This is the system. Okay. Now when this coal is a system and this is the surroundings. This is the surroundings here. So system and surroundings. And this is just a coal. Between coal, piece of a coal and the surroundings, there is no boundary at all. Yes. This entire coal piece, a particle of coal, is nothing but system. So between coal particle and this surroundings there is no boundary. Like there is no, boundary of copper, no boundary of zinc, nothing is there. So it's just a coal piece. So then I can draw one imaginary boundary. One imaginary boundary I can draw myself. So I can imagine that there exists a boundary between coal and the surroundings. Yes or no? So my dear friends, this coal is your system. Okay? And what is outside is the surroundings. Now you will be thinking that coal is under experimental. Coal should be under experimental investigation. Means you may be studying the properties of coal. If you are studying the properties of a coal, let us suppose, that means coal is under experimental investigation. Because you are reading the properties of coal. Yes, how does it burn in atmosphere? Yes or no? Coal is nothing but carbon. So you can study that how does coal burn in presence of oxygen. So that means coal is under experimental investigation. That means coal has become the system. And whatever is outside, it becomes what come on? Surroundings. Rest of the universe is the surroundings. So this imaginary, line which I have drawn, the dotted area, is nothing but it is your imaginary boundary between system and surroundings. Now, once again I am telling you how coal will be your system. If you study the properties of the coal, if you see how the coal burns in atmosphere, yes or no? In presence of oxygen, because coal is carbon only. So that means the coal will be under experimental investigation. Yes or no? So it becomes the system. In this marker, my dear friends, this is the outer boundary of the marker. If I open it up and I will start you know what, studying the properties of the ink which are inside the marker. So ink becomes the system. Yes or no? And this outer cover becomes, you know what, the boundary, and the entire thing becomes what? Come on, surroundings. The ink inside the marker is the system, and this is the boundary, and it's a real boundary. This plastic cover is a real boundary, and this is the surroundings right out here. I hope, my dear friends, you can easily find out what is system and what is surroundings. Let us suppose if I will take one beaker from here. Let's suppose I am taking one bottle from here, and this outer, you know what, covering, this one, it's a glass only. This is the boundary, and this is real boundary. And if inside this particular bottle we have dilute sulfuric acid, that dilute sulfuric acid, if I am doing my experiment on dilute sulfuric acid, then this dilute sulfuric acid will become the system, and this glass is the boundary, and whatever the area is around it, like this rest of the universe, that is the surroundings, my dear friends. So my dear friends, let's talk about one or two more terms here. We can have diathermal or diathermic wall. Diathermal wall, or we may have an adiabatic wall. So that wall is nothing but it's a boundary. So please try to understand. Now boundary can be your diathermal, or it can be what? Adiabatic. Correct? So here diathermal, okay, this wall, it allows exchange of heat between system and surroundings. Exchange of heat between system and surroundings. Now adiabatic, it does not allow exchange of heat between system and surroundings. So my dear friends, look here. If it allows the heat exchange between system and surroundings, correct? So if you look here, let's suppose this wall is here, a diathermal wall. Which wall is this? Diathermal wall. And now inside what we have, which system we have inside here, my dear friends? Here we have, okay, a particular system. It may be a gaseous system, it may be a boiling water, it may be a burning coal, it may be acid-base reaction, it can be anything inside. Yes? Now if this is a diathermal wall, there is a possibility that heat can come out. So heat is coming out from where to where? System to surroundings, heat is coming out. If within the system temperature is very high, if system is at high temperature, then heat will flow from system to surroundings. Yes or no? Now if the heat is more outside, yes or no, then that means heat can flow also from where to where? Surroundings to system, depending on if surroundings is hotter than the system. If surroundings is hotter than the system, then heat can flow from surroundings to system. If system is hotter than what? Surroundings, then what will happen? The heat will flow from system into the surroundings. So in first condition here, if we look at this condition, here system is hotter than what? The surroundings is hotter than surroundings. And in second condition, if we see, the surroundings is hotter than the system. So look here, the heat is flowing from system to surroundings, which means it's a diathermal wall. This wall is diathermal. It allows exchange of heat between system and surroundings. So this wall is diathermal wall, correct? But now, if you look at the same thing here, so my dear friends, if we look at the same thing, let's make it as a closed vessel. Okay. Now we have a system here and we have a surrounding here. Let us suppose this wall which I am making here is yours adiabatic wall. This is the adiabatic wall. Then what will happen? Heat wants to come out from the system. So do you think that heat will come out? The heat which is present inside the system, will it come out or not? Here it comes out. Have a look. Let's write it like this. Heat is inside the system, it comes out. But here heat wants to come out. But will it come out or will not come out? Will not come out into the surroundings. Reason? Because this wall which is here, it is adiabatic wall. It does not allow exchange of heat between system and surroundings. So heat will come out or will not come out? Heat will not come out of the system into surroundings. Or heat will not go from surroundings into the system. Are you following, my dear friends? Even though the system may be at high temperature, there may be high temperature inside the system, and there may be low temperature in the surroundings, but still heat will not flow. Why heat does not flow? Because this wall which is here is nothing but it's an adiabatic wall. It will not allow the exchange of heat between system and surroundings, or vice versa, that is surroundings into the system. No exchange of heat is possible because this is adiabatic wall. And if you look at this wall is diathermal wall. That means heat can come out from system into surroundings. But provided here, I will tell you, the system which is here, let's mention it like this. The system should be hotter than, we can see it is colder. It's hot and it's cold, we can write it like this. So heat will flow from where? System to surroundings. Like heat is flowing from system into surroundings. Correct? Now, even if system is hotter than what? Surroundings, heat will not flow, because between system and surroundings there is a boundary, and that boundary is nothing but what? Adiabatic wall. It will not allow the heat to come out, and it will also not allow the heat to go inside. I hope everybody has understood, my dear friends, these two boundaries, diathermal and adiabatic. Diathermal can be also called as conducting wall because it conducts heat, and this adiabatic wall can be also considered as non-conducting or insulator directly. Can be considered as insulator. It does not conduct. I hope everybody has understood. So my dear friends, now we will be talking about the types of thermodynamic systems. We have open system, closed system and isolated system. Let's talk about the open system first. So if we look at the open system, what happens? There is an exchange of matter and energy between system and surroundings. So my dear friends, in open system there is an exchange of two things. One is matter, that is mass, and the energy between system and surroundings. Now let's have a look. If we take an open system, okay, have a look here. Let us suppose this is the open copper vessel. Yes? And inside this copper vessel, my dear friends, let us suppose I will keep the boiling water. Inside this copper vessel there is a boiling water. So inside there is a boiling water, which means actually water is present at high temperature inside the copper vessel. Correct? So what happens? It's open here. When water is present at high temperature, yes or no? And why from this boiling water happens actually? You can also write it down like, if we apply the heat, let's suppose if we are applying the heat to this vessel, yes, my dear friends, then you can, this water, if it is cold, it will boil up. So remember that particular point. Already you have heated water, okay? Now it is the boiled water now, okay? And that boiled water you have placed it in which vessel? You have placed it in the open copper vessel. So which water you have placed it in the open copper vessel? Boiling water. and this boiling water will produce the vapors or not, and these vapors will come out. Yes, and now my dear friends, you know that this is the surroundings and this thing is your system. So you have seen right out here, my dear friends, what is coming out? Vapors are coming out. These are the vapors. Which vapors are those? Water vapors. Now water vapors are coming out from system into the surroundings. So first thing, water vapors. You know that this water is boiling water, it is at high temperature, so vapors are coming out. So water vapors, okay, travel from where? System into, or travel from system to surroundings. So when water vapors are traveling from system to surroundings, we call it as matter exchange. Second thing, this wall of copper vessel, we know that this is made up of copper, it's a copper vessel, and copper vessel, wall of the copper vessel is nothing but, it is diathermic. So we have a diathermic wall here, or I can also call it as conducting wall. And you know that inside there is a hot water, there is hot water inside. So when the water is very hot inside, so what will happen? The heat will flow through this wall and it will come out into the surroundings. So heat is coming out because inside this vessel there is a boiling water, hot water. So this is at high temperature and surrounding is at low temperature. So my dear friends, heat is coming from system into the surroundings. So there is an exchange of heat between system and surroundings. So understand, my dear friends, and this heat exchange is possible only because of which wall? Diathermic wall or conducting wall. When this diathermic or conducting wall is there, then only there is a possibility of exchange of heat from system to surroundings. So my dear friends, water vapors travel from system to surroundings, that is a matter exchange, and exchange of heat between system and surroundings through which wall? To diathermic wall. So both the things are happening here, my dear friends. There is an exchange of matter and energy. Matter is here nothing but your water vapors, and this energy is nothing but the heat. So both things are exchanged between system and surroundings, and we call it as open system. So open copper vessel is nothing but it is our open system. I hope, my dear friends, you have understood this thing, correct? So let us take one more example. Look here. Now I will take the same copper vessel. Inside the copper vessel, let us suppose I have now which water? Cold water is here. So this is our system. Correct? And now this is the surroundings. This is the surroundings here. And this wall is your diathermic wall. Diathermic wall. And you know that system contains here cold water and surroundings will be hotter than the system. In this case, the surrounding is hot and the system is cold. So when surrounding is hot and system is cold, then heat will flow from surroundings into the system. So there is a flow of heat from surroundings into the system. So heat exchange is there. Yes? One more thing. Have a look, my dear friends. One more thing we'll discuss here. So which water is inside, my dear friends? We know it's a system only. And which water is inside? Everybody knows that this is the cold water. Okay? Heat is flowing from system to surroundings. First thing. Second thing, in atmosphere, let's suppose this surrounding means atmosphere only. Let us suppose in atmosphere we have carbon dioxide gas, we may have nitrogen gas, we may have oxygen gas, and gases can dissolve in cold water. Remember, dissolution of gas In cold water is more. So now carbon dioxide gas from where? Surroundings. This carbon dioxide gas from surroundings dissolves in the system. What is system here? Cold water. So first point, carbon dioxide gas dissolves, or we can say travels from where? Surroundings to system, or from surroundings into system. Yes, that is, and dissolves into the cold water, and dissolves into cold water. That is nothing but its matter exchange. So now the matter is coming from atmosphere and dissolving into the system. Matter exchange. What about the heat exchange? Heat exchange is also happening. Heat is traveling from where? Surroundings into the system. So here heat travels from surrounding into system. Correct? Through which wall? Through diathermal wall or diathermic wall. So both the things are happening here. So this is our, let's suppose this is the open, vessel of copper, of aluminium, of zinc. It can be a copper vessel, it can be aluminium vessel, it can be zinc vessel. So anything. So my dear friends, these were the examples of open system where there is an exchange of matter and energy between system and surroundings. After this, we will go into the closed system. What is closed system, my dear friends? Have a look. Let us see. If we talk of closed system, here will be the exchange. There exists exchange of only energy between system and surroundings. Means matter is not exchanged, only energy is exchanged. So my dear friends, there exists exchange of only energy between system and surroundings. So you can understand here, there is no exchange of matter. There is no exchange of matter between system and surroundings. Between system and surroundings, there is no exchange of matter. You can remember this point as well, but this is enough. There exists only exchange of energy between system and surroundings. Let's take an example here. Let's take, if we take a closed copper vessel, let's suppose we are taking here a closed zinc vessel, copper vessel, anything. Copper vessel, it's closed. When it's closed and I have here which water, let us suppose. I can have here boiling water or I can have here cold water, you can write down. Inside there is a boiling water. Now heat wants to go out and this is our system, everybody knows. This is the system. Now heat wants to travel outside, it will travel, that's possible. This is surrounding and this is system inside. Okay. Now this wall is that diathermic wall. Now do you think this boiling water vapors are also present inside or not? So water vapors are also present inside. Do you think water vapors can come out or they will not be able to come out? Water vapors cannot come out, my dear friends. Let's suppose this is the heat. Heat is coming out through diathermic wall. But what about the water vapors? If the water vapors are here. If water vapors are here. Do you think water vapors can come out or not possible to come out? Not possible to come out. Why? Because the system is closed. When closed system is there, water cannot go out or any gas cannot come inside. That means there is no exchange of what? Water, or there is no exchange of gas between system and surroundings. That means there exists exchange of only energy between system and surroundings. So only heat energy can come from the system into the surroundings. Yes? And second thing, if it is a cold water now inside the system, we have a cold water. Now if you have a cold water, then reverse thing will happen. What will happen, my dear friends? Now heat can move from where? Surroundings into the system. So heat can travel from surroundings into the system if there is a cold water inside. Now what is the point here? Point is that now if you want the carbon dioxide gas to dissolve into cold water, it's not possible. Why? Because system is completely closed. So there is only the possibility of exchange of energy between system and surroundings. No exchange of matter between system and surroundings is possible. So no exchange is possible of a matter because system is closed. So after that, we will talk about the isolated system. So what is an isolated system? Let us see. If you talk of isolated system, my dear friends, very simple. There is neither exchange of matter nor exchange of heat energy, we can say, between system and surroundings. Now look here, my dear friends, if I will take an example of thermoflask. Thermoflask, we'll take an example of thermoflask. Correct? What happens? Have a look here, my dear friends. If this wall of the system here, if this wall is adiabatic, I have already told you. Adiabatic basically means boundary is adiabatic here. No exchange of heat is possible. So that means it's an insulator. Correct? So adiabatic wall means no exchange of heat is possible. No exchange of heat between system and surroundings. Correct? Let us suppose inside we have any substance we can take on either cold water, hot water. You can take some chemical reaction also inside happening. Okay? My dear friends, let us suppose one chemical reaction is happening here between sodium hydroxide and HCl, between base and acid. One chemical reaction is happening here. In that chemical reaction, what happens? You will be getting NaCl plus H2O. That means you will get a salt and water. And during this reaction, there will be a production of heat. Heat energy is produced. So my dear friends, a chemical reaction is taking place here. So a chemical reaction takes place between acid and base. And due to that chemical reaction, there is a production of heat. So heat energy is produced here. Do you think this heat can come out or will not come out? See here, this is a chemical reaction. In this chemical reaction, heat energy is produced. So my dear friends, this chemical reaction is taking place here inside. This chemical reaction. What is produced? Heat energy. So this chemical reaction gives heat energy. This heat energy can come out into the surroundings. Possible or not possible? Not possible. Because wall is adiabatic wall. There is no exchange of heat. Because wall is an insulator. So it will not allow the heat to come out. Because it's an adiabatic wall. So once again I am telling you. So inside this there is a acid base reaction. Which reaction? Acid base reaction is taking place inside. Due to that acid base reaction we are getting which energy? Heat energy. So heat energy is produced here. Now this heat energy wants to come out of the system. But which wall is here? Wall is adiabatic. So will it come out or will not be coming out? Will not come out. Not possible at all. Heat energy cannot come out because wall is adiabatic wall. So heat energy produced during this acid-base reaction will not come out. So now, my dear friends, this is your surroundings. Do you think now, what is the substance produced here? Salt and water. Yes or no? Do you think if salt and water is produced, let's suppose water is here now present. Correct? Because salt and water are produced, let me take water. Water is here. And do you think any gas from surroundings, let us suppose I have a carbon dioxide gas. Do you think this carbon dioxide gas can come and dissolve in this water? This water? Do you think this gas can come and dissolve in this water? Possible or not possible? Not possible. Why? Because system is closed. This thermoflask is nothing but it's a closed one. Yes? But we call it as actually insulated. We call it as insulated. You can call it as it's closed. It's insulated. Closed and insulated. First of all, it's closed from everywhere. And it's also insulated. Insulated means it's an adiabatic wall, it's an insulator. No exchange of heat. So matter cannot go inside. Or no matter can come outside because its boundary walls it's closed from all the areas. Two things are here. It's closed and it is also, insulated. So when closed plus insulated, both things are there, we call it as isolated system. So thermoflask is nothing but it's an isolated system. So my dear friends, if you look at thermoflask, it is closed. Okay. Second thing is that no gas can come inside or no substance can move from inside to outside. There is no exchange of matter. Second thing, the heat produced during this chemical reaction wants to go out, but there is a adiabatic wall. It's an insulator. It will not allow the heat to come out. That means neither heat is coming out, so nor matter is exchanged. That means it's an isolated system, my dear friends. So what is the open system which can exchange both heat and matter with the surroundings? System, between system and surroundings. Closed system, it can only exchange the heat if the wall is diathermic. And what about isolated system? It can neither exchange heat nor matter with the surroundings. So I hope everybody has understood. So with this, I would like to end up today's session. Meet you tomorrow. Have a great time. Thank you.